Okay, welcome to lesson 1.3 on linear modeling. This one is going to require a graphing calculator. So as you can see here, I have the one that is online, though you guys can use this one, or obviously you can use a physical graphing calculator, but it is necessary for this lesson. So if you don't have one, pause the video and go ahead and grab one. So this is all about how we can use linear equations in like real world applications. And the first thing starts off with just understanding what like a particular situation, what the graph may actually look like. So number one says a person gives $20 per week to a friend to repay a $200 loan. So obviously if you took out a loan from a friend for $200 and is paying them back, then the loan balance would go down from $200, and so the only one that is B. An employee receives $12.50 per hour plus $2 for each unit produced per hour. So this is somebody making money for every hour. Yeah, excuse me. So here, obviously, it's going to have a slope of $12 per hour, and then $2 for each unit produced per hour. So you would actually see it, start there at $12.50 and then go up from there based on the number of products they produce per hour. So that one is going to be C. Number 3, a sales representative receives $30 per day plus for food plus 56.5 cents per each mile driven. So obviously you're going to start out at $30 per day and then go up from there for every mile that you've driven. And the only one that's at 30 starts at 30 and goes up is A. The last one, a computer was purchased $750, and then the computer actually depreciates in value over time by $100, so the value of the computer will actually go down over time from $750, and so that one is D. So just recognizing what a particular situation looks like graphically. Here is where the graphing calculator comes in. So back in Algebra 1, when you were given 2 points like this, you would, and you were asked to find the equation of this line. When you were given 2 points, you used to have to do point slope formula. You would take 1 point, do the other point, and you would find the slope. Then once you had the slope, you would put it into point slope formula, use one of the points and the slope to find the equation of the line. But what your Algebra 1 teachers didn't tell you is that your calculator can actually do this for you without you having to do any sort of math, I guess. So it asks you to write the equation and then interpret the slope. So we're going to write the equation. So on your graphing calculator, in order to do this, you're going to need to find the stat button. The stat button is sort of in the middle of the calculator. It goes alpha and then the x, t, theta, n, but then stat. So you see stat right there. It's highlighted in red now. We go to stat, and then we're going to go to edit. We're going to edit our stat. And then it should look like this. And the list should be empty. If for some reason the list is not empty, there are numbers in there, you simply just hit the delete button there, and it will clear. You can clear out the numbers, or you can go up to the top of the column there and then just hit the clear button, and it will clear all the data as well. So what you do is you see L1 and L2. Those are called lists. If you use list 1 as the x values and list 2 as the y values, you can actually tell the calculator to calculate a regression line, which is the equation of the data that you put in. So if I do 0 for my x and then 360 for my y, and then I do 6 for my x for the other point and 0 for my y on the other point, those are my 2 points. I then can click stat again And this time, go to Calculate, which is the second menu here, and go down to LinReg, which is short for linear regression. A regression model is simply a computer-calculated line of best fit, the equation of a line. And so you can use this with as long as you have at least 2 points, you can use this line of best fit calculator. And so we hit enter, and it's just asking, is X list 1 and Y list 2? Yes, it is. And just go down to calculate. And you'll see that there's the equation. Y equals mx plus b, though they use a instead of m, but it's the same thing. So my equation will be y equals negative 60x plus 360. When we go to interpret the slope, you kind of have to take into account like all that's going on here. This is travel distance. This is the distance and over time. It starts at 360 and then goes down to 0. So obviously what this tells me is that you're returning home. You were away from home, and the distance from home is going down as you're flying back home, or driving, I guess. So what we can see here is that maybe since the distance, you have miles and hours, this could be then miles per hour. Since slope, m, is your change in y over change in x, the change in y is miles, the change in x is hours, so you have miles per hour. So essentially, you're driving 60, so driving, let me give myself some room here, driving 60 miles per hour, or mph, however you want to do that. Or you're gaining, you could also say you're gaining, your distance from home is decreasing by 60 miles per hour as well. We could try the same concept here, homework grade in percent versus completed assignments. So obviously the more completed assignments you do, the higher your grade goes. That's what this is telling us. But we can calculate the exact equation here by, again, going to stat and edit. Now, again, I can delete these. I could just hit the delete button, and that will delete them. Or you could go up to the top and hit clear. That will also delete them. Then we put these in here, x and y. It doesn't matter which point is first. So I'm going to do 10 and 85 first, and then 20 and 95. And then again, stat, I go to calc and linear regression. Yes, this is all true, blah, 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 calculate, and there is my slope and y-intercept. So y equals 1x plus 75. And that's my equation. And since we have completed assignments and homework, again, homework is the y, which means basically with the slope of 1, it means that for every, your homework grade goes up, homework percent goes up 1% for each completed assignment. And that's how you would interpret that slope. Now those are relatively easy because there's just 2 points. You can do it pretty quickly. What linear regression really works well with is dealing with a lot of data. Here you have the length of your femur and its relation to your height. Your femur is the biggest bone in your body. It's in your leg. And obviously you could probably tell that the bigger the bone is, maybe the taller you would be. But we can actually figure out the relationship between femur length and height in the form of an equation. So here is the directions to tell you exactly what I just told you above, except now we're going to type in all of these numbers in here. So stat and, not calc, stat and edit. We're going to delete these. When there's only 2, it's just easy to hit delete. And now I'm going to put all these in there. So I have 40 and 45 and 32, 50, 37, and go quick, and 30, and 34, 47, 45. Now if I did it right, the number should match up here. 170, 183, 151, 95, 162, 174, 141, 151, 185, and they do match up. Even numbers. Okay, now, so we could do the same process. This is a bunch of data here, but we can go the same process, stat and calc, and go to linear regression. Yes, list 1, list 2 are x and y, calculate. And so we get a slope and an intercept. And we don't have to, write all the digits here. We can make this easier. It says write your equation, so that's what I'm going to do here. So y equals, I'm just going to do 2 decimal places, and then plus, this one looks like 2 decimal places actually just places it up to 65. So there's my equation. So it looks like since femur length, it doesn't give us any, in centimeters. So for every 2.6 centimeters our femur length is, that's how many centimeters we grow in, for every 2.6 meters in height we grow, then our femur is growing 1 centimeter. So it's 2.6 over 1 is the slope, and it's y over x, so it should be height over femur length. So then the next thing here, one thing that you do with linear regression as well is a thing called correlation coefficient. So correlation coefficient basically tells us how well the data matches the equation of the line. How linear is our data? The closer to 1, the better. We like it to be closer to 1. That is going to be closer and closer to a perfectly linear data. If it's further from 1, then it is going to be less and less linear. So you have some examples here. So perfect 1, if I were to draw the line of best fit, it would pretty much go through every single one of those dots. That would be perfectly linear. This is obviously the best. When we get a little bit away from 1, then, by the way, the correlation coefficient goes between 0 and 1. Well, 0 and 1 or negative 1 if it's going down. When I draw this line of best fit, notice how not all of them are there, but they're all still pretty close. Point A is still pretty good as far as linear. And then when I get to far away from 1, now a lot of the dots are pretty far off from the line. You could still tell the trend is increasing here, but it's not as strong as it would if it were like 0.8 or something like that. And obviously it was 0 correlation. I have no idea if this data is going up or down or where it's going. So this obviously is the worst. And then when you get negative, the only thing that negative does is it just means your data is going down. So this is still going to be a poor correlation. But when you go down to negative 0.8, this is really good. I mean, that's really good. So we don't pay attention really to the sign. The sign just tells us if it's going up or down. Negative 0.8 is just as good of data as positive 0.8. It's just going up or down. And obviously negative 1 is perfect. Oh, that's a terrible line. Is just as perfect as positive 1 is as far as linear goes. Now, how can we get the calculator to give us this R? Notice how when I do linear regression, I don't see the R. We can do something to our calculator to have it make sure that the R does come up. And so what you would need to do is go to mode. You can see it's highlighted in red there, mode. And then what you want to do is go down to where we see stat diagnostics. If you notice, stat diagnostics is off. So I'm going to go to on and hit enter and turn it on. Now, when I go to stat and calc and go to linear regression, and calculate, I get the R value. Now, it's important to note here that we do not look at R squared with linear equations. We only look at R. So you need to ignore the R squared. R is what we're talking about here, R. And the R, or correlation coefficient, in this case would be 0.99. So obviously that is very good. Remember, the closer to 1, the better. What this tells us is that our data, as far as height in relation to femur length, is really linear. It's really close to being linear. And so it's really good data, really good linear data. And then what we can also do is use our model. So this equation right here, we can use our model to make predictions. So let's say we measured a femur. Let's say we found some human remains. We found a body that was buried or something like that. But we didn't find all of the body. We just found a few bones. If we find the femur and we measure the femur, we can then use the femur length to estimate how tall the person was based on this data. So if we dug up, some bones and found a femur and it was, 35 centimeters long, about how tall would this person be? Well, you just simply take the 35 centimeters and plug it in. So I can do, 2.60 times 35 plus 65. And I could do the math there. I don't have, right here. So 2.6 times 35, and then add the 65. So we could estimate that this person was 156 centimeters tall. So that's how we use that. That's essentially linear modeling in a nutshell. We can do here, we could do these problems right here, same thing. Now these ones don't give us actual coordinates, but we can still type them in. So I can type in this one, this one, this one, this one, this one. So I'd have 5 points. So stat and edit. Now watch, this is where clearing them out makes it much better. Go up to the L1, hit clear, enter, done, clear, enter, and done. Much faster. So the first point that is over here, that looks like it's 1 and 5. So 1 and 5. And then I have right here 2, 2. And then I have right here 3, 1. And then this one is 5, 2. So 5, 2. And the other one's 5, 5. And so I can figure out, obviously you can look at this and go like, this is probably not going to be very good correlation because I have no idea if this data is going up or down, maybe slightly down, but I can't really tell. So I go to stat and calc and linear regression here and calculate. You can see that the correlation coefficient is terrible. It gives me an equation of, I should probably use the pen. The line of best fit looks to be like negative 0.078 x plus 3.25. So it looks like it's like something like this. Something like I guess that's what it's doing. The correlation coefficient is negative 0.07. That's really far, that's really close to 0. You remember, the closer to 1 or negative 1, the better. That's really bad. So this would be poor. You could use the language they use up here, which is either, I would say, no correlation to low negative correlation. This is poor, definitely poor correlation. And you could probably guess that this one right here is going to be pretty near perfect, if not perfect. And so you can use the same strategy there to find that one. But that is linear modeling there in a nutshell. So if you have